To finish up our electricity and magnetism unit, we have to talk about magnetism. For us in Regents Physics, we focus very little on magnetism. There's no math, which is what you guys are going to definitely enjoy, but more so the conceptual aspect of it and how magnetism relates to electricity. So when we talk about magnetism is what we call a field force, meaning that if it's in a field, we can associate direction. So when we talk about magnetism, we talk about it acting over a certain distance without coming into contact. You all have been around magnets before. You've all felt if you take two magnets and try to push them together, sometimes they're going to stick immediately together. Other times, as you try to move them around each other, you almost feel as if there's almost like a ball between them that you kind of push your magnets around. That's what we talk about being in a field and the different poles that we're going to be discussing. So magnets produce fields, and these fields are what, like we said, you are feeling as you're trying to get your magnets to move together. And these fields influence different types of metals. And in particular, we talk about iron, nickel, and cobalt. When we talk about magnetism, we, like we said, are relating this to electricity. So we'll discuss how electricity and magnetism do relate to each other today. And these magnetic fields, when we create them, we're able to draw them as different field diagrams. And these field diagrams have field lines that travel from the North Pole to the South Pole. So just like when we talked about in electricity and we said that if you take a positively charged test charge and you place it around different charges, we can see the way that the electric field map will be. And we said that you always go from a positive to a negative. So as we draw our field lines, it always goes out from a positive into a negative. The same type of thought process kind of goes when we're talking about magnets, in that you're always going to go from your North Pole into your South Pole, always. We represent these field lines around magnetic objects. So never through, only around the object as a surface around them. And as we draw these, we're able to draw them just like we did electric field lines. So one thing that we need to make sure we understand is that field lines do not ever cross each other. Just like when we talked about electricity and we drew our electric field lines and we said that they cannot ever cross, they will just bend as they move around objects. Same thing with this. So your field map is going to look very similar to that of when we did electric field mapping. It's going to look very similar to that for magnetic fields. So as we have our magnetic field, like we said, we always go out from north into south, always. But we're going around your magnet. So this picture represents a bar magnet. So a magnet, not like a little circle magnet that you have that sticks to your refrigerator or something like that, but like a strong bar magnet that literally looks exactly like this, where one end is a north, one end is a south. And these magnets, it creates a field all the way around it. So we're able to draw a whole bunch of field lines that go out and around our magnet. However, we know that these field lines do not just stop on the ends. We know that something has to be going on the top and bottom of your magnet. And for that, that's how we draw the bending of our field lines. So they look something like this. We have that on the bottom. We also have the same going on the top. We can have infinite number of field lines, of course. We are just going to draw a couple of them like this. So again, understanding the fact that it goes out from the north into the south. You have your arrows on here representing the direction of your field lines, exactly like what you see here. Always going out from north into your south. We can also talk about magnets in terms of compasses. So if you have on your phone, if you open up your phone and you go to the compass app, That compass, of course, using satellites, but that compass is showing you the direction always going to be pointing north, right? So the little arrow on your, the little arrow that is on your, that pops up always is going to be pointing to the North Pole, right? That's what we always say. Okay, well, when we talk about compasses, we're talking about the Earth being a magnet and how the magnetic field of Earth works. So the Earth is a magnet that is able to interact with other magnets. The north end of your compass magnet is drawn to align with the Earth's magnetic field. So the Earth itself has a magnetic field, and it works directly in line with the way the compasses work. Because the Earth's magnetic north pole attracts to the north end of other magnets, it's technically the south pole of our planet of Earth's magnetic field. So what we mean by that is, this here is what we say in terms of Earth. It's the North Pole. And we say, let me zoom out here so we can see what's happening. And we say that down here would be the South Pole in terms of Earth. Right? We always say north is on the top, south is on the bottom, and we're good with that. That's the way we learn it, and it's great. That's the geographic North and South Pole. But because we know that our compass always points north, and our compass is always going to point, if we're talking about the Earth here, it's always going to point into the North Pole and away from the South Pole. Well, then, if it's pointing into the north, that doesn't really line up with what we just said about in terms of physics and the north and south pole of a magnet. So when we're talking about the magnetic North Pole and the magnetic South Pole, really what we have is this up here is the South Pole in terms of, we'll say, physics. And down here is really the North Pole in terms of physics. So don't get confused with the fact that we know north is on the top and south is on the bottom in the Earth. That's true in terms of geographically, but in terms of physics, in terms of the magnetic south and north pole, it's switched, or it's different than that of what we call Earth. So when we talk about the magnetic field lines around Earth, we do it the same way as we have before. So we have your field lines going out from the North Pole into the South Pole. But again, we know that these field lines are going to come into contact, of course, where it's going out from the north into the south. And again, it looks something like this. It's, of course, on both sides. Again, you're not like ever graded on how beautiful you're able to make these pictures. It's just as long as you can understand the concepts. So you're always going out from the north into the south. And again, south and north poles in terms of geographic and physics are different. Earth's magnetic field reverses once about every 200 years, which means that it's constantly flipping throughout those 200,000 years. The magnetic, we'll say the core, is about 4,000 miles into Earth. And so as the time progresses, you're able to, the rotation and everything all combined, the magnetic field is going to constantly be flipping. So as far as where these magnets come from, we have a physicist, actually, I will tell you exactly, from Denmark, Hans Christian Ørsted. And this physicist, he worked with physics, he worked with chemistry, and what he did, he discovered that a magnetic needle, so meaning that of due to magnets or to a compass, aligns itself perpendicularly, oh my goodness, excuse me, to a current carrying wire. So meaning to a wire that is currently carrying a current or currently has a charge, it is able to come into contact with a magnetic field. And if you bring a compass over to it, you would actually see a changing magnetic field without actually having magnets. And the same would be true if you had a magnetic field, being able to take a wire and push it through that magnetic field, you're able to induce a current. I actually have posted videos since we're not in school or anything, and I can't actually show you this. I posted videos that I definitely encourage you to look at. They're very interesting, and it talks all about this. So there's some YouTube videos. Definitely check them out. But for this, so Ørsted, this physicist, what he did is he moved a charged object, and he saw that that makes a magnetic field. So exactly like we said, and that's something that's called induction. We talked about induction when we talked about electroscopes and being able to induce something to make it happen. That's the same kind of concept here. So this picture that we have here, this is for a wire, a current carrying wire. Obviously, it has an electron flow, and I just happen to say that it goes to the right. So this is actually using something that's called the right-hand rule. And again, I'm going to post a video on this because obviously I'm not sitting in front of you to be able to show this to you. But what this is going to show you is the direction of your magnetic field. So what you do is you take your right hand, and if you don't get this from me talking about it, definitely look at the video and see how to do this. But you take your right hand and literally put it in front of the screen exactly how you see it here. So your right hand, your palm should be facing towards you. The back of your hand, where your nails are facing towards your computer screen or your phone screen. Okay. The way this works is you take your thumb, and your thumb points in the direction of the flow of your electrons, or the flow of your charge. So as we're looking at this right now, you should have your thumb being pointed to the right, your palm is facing up towards you, and your fingers, your 4 fingers, as you curl them, so meaning you curl them to kind of almost create a fist, the direction of your curl is the direction of your magnetic field. So if you're doing this the right way, you should have your thumb pointed to the right. Your fingers are coming towards you, which means that the direction of your magnetic field is coming out around the wire and then going to go traveling back in. So it looks exactly like this. Again, if you need to see a video on that, by all means, check out the one I posted. But again, your thumb is the direction of your, I'll write this down here for you. Your thumb is the direction of your electrons, or the direction of your current, and your fingers curl in the direction of the magnetic field. And you should have them coming out towards you, such that if you were to go all the way around, it would create the pathway that we drew, these 3 arrows. Lastly, when we talk about electromagnetic induction, electromagnetic, electricity, and magnetism together, this is where you have a conductor, so something that is able to conduct electricity or allow for charge flow, is placed in a changing magnetic field, causing the production of a voltage or a potential difference that we call V across that conductor. This process of electromagnetic induction in turn causes an electrical current, or a flow of your charge, so an electrical current, which is our I, inducing that current. So we have, again, a magnetic field. We have a conductor that when placed in between your magnetic field, you're able to create a charge without actually having any type of electricity. You're creating it. You're making it from just a magnetic field. So when we talk about these magnetic fields, we have a couple of different pages here as far as some practice. So there's some practice here. We're going to do a couple of these here together, and then the rest you can do on your own. So for instance, if we look at, say, number 2, so I'm going to just pick and choose some of these here to look at. So we look at number 2. Both of these are north ends of a wire. Both of these of a magnet. Both of these north ends are going to have your magnetic field be coming away from your magnet. So we know that 2 norths are not going to attract, right? So these magnetic field lines must, it should be a solid line, must be repelling away like this. Again, our magnetic fields do not touch, they don't cross. So it should look something like this. Of course, all the way on the outside as well, you do have, a repelling of, or not a repelling, your magnetic field coming out and away. But really, I would say what's the most important is seeing how your field interacts in between. Again, also in this location right here, let's get a different color. In this location right here, we know that because you have your field that is constantly pushing away, in the middle, there is no field because there's nothing that would exist there because your field is constantly trying to repel apart. So all of these are practice here. Like we said, we can look at this horseshoe. This is a horseshoe magnet. And a horseshoe magnet acts in the same way, except for the fact that it's a horseshoe, not a bar magnet. So you have your magnetic field that is going to go from the north to the south, as always. And it's going to continue to move in this direction like this. Same thing on the inside. When it gets to the middle here, it will start to bend as your magnet starts to bend. But yeah, so it's always going from your north to your south. So all of the rest of this is just to practice. Let's look at number 5. Let's do that one together as well. So for this, you have the north and the south that's going to want to that's going to go out from the north into the south for each magnet, right? So you have the bottom magnet that's going to look like this on the top and the bottom. Okay. You also have the same thing going on the top, except now you're going the opposite way because you're still going into the south as always. So it looks something like this. Okay. You have the same thing again on the bottom here. So going from the north to the south. You could totally draw more. I'm just getting very close, so I'm going to leave it as that. You also have going from the north to the south this way. Okay. We have it on the other side as well. Just making sure that you're paying attention to the direction of your field lines. So it looks like this. Okay. And it looks kind of messy and it looks kind of like, what do all these lines mean? But that's why we're drawing the arrows, to show the direction that we are attracting or repelling in terms of our magnets. So the rest of this page you're able to do similar to the next page. The other thing that we need to discuss is that for compasses and compass directions in terms of our magnets. So when we talk about these compasses again are showing you in terms of the direction of your in the direction of your field. So compasses always point north. Always, 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 always. And when we talk about our compass, we talk about it pointing north, and we literally just drew it with a little arrow like this. So we're indicating what direction we're going. So my advice is, as you go through and you're doing these compass directions, you want to make sure that you're showing the easiest way is to think about what the field would look like at that point. So here's your magnet. The circle is where we're going to draw our compass direction. So literally, if you draw from this north, we know that your field is going to want to go away because we always are going away. So that means that my compass itself is going to be pointing in this direction. So it points in the direction of your field. Again, if we go with, let's say, for the south, we know that my south always points inward. The field always points inward. And if we do that, then we know that my compass always has to point this way when next to a south. If you look at a different one, you could figure out all of those. If we look at, let's say, number 7, for this, again, the easiest way to do this is to just consider what does your field look like? So you're literally going from your north to your south. from your north to your south, with here's your arrows here. And all you need to do is draw in exactly what you see. So as I look at this circle on the right, my field is going away from my north. So it looks like this. As you look at the one on the left, it's going into the south. And then when you look at the ones on the top, as you carry through with the line that you drew, well, when you get to the top or the bottom one, they're both going to the left, like exactly to the left. So the only way that you would have them curve, like, or not curve, but be at an angle, would be, say, if you had one like here, right? If you're talking about this one, well, then it is clearly going at an angle. Or if you have like one right over here, it's clearly going at an angle. It's not perfectly horizontal. So it just depends on the placement of them.